Welcome to The Explainer. Today we are digging into the hidden science that keeps your music from sounding like mud and your videos looking sharp. It all comes down to a battle of timing, phase delay versus group delay.
So let's start with a really fundamental question. Why is it that a perfectly good signal, like a song or a video feed, can get all distorted and messy just by passing through a system like an amplifier or a cable? What's actually going wrong?
All right, to really get our heads around this, let's use an analogy. I want you to picture a complex signal as a team of runners getting ready for a race. Each and every runner is a different frequency. You've got your low bass notes, your high treble notes, and everything in between, all lined up and ready to go. Now, for that signal to come out clean on the other side, all those runners need to stay in their original formation. But what happens if some runners get slowed down more than others? The bass runners arrive late while the treble runners are early. The whole formation falls apart. It gets messy. And that chaos, right there, is distortion.
Okay, so if that's the problem, how do we prevent it? Well, first we have to be able to measure it. And it turns out we have two very different kinds of stopwatches for the job: phase delay and group delay.
So first up is phase delay. Think of this as putting a dedicated stopwatch on every single runner in the race. It measures the absolute time it takes for each individual frequency to get from start to finish. Simple enough, right?
But then we have group delay, and this is where it gets really clever. Instead of timing each individual runner, group delay uses a single stopwatch to time the entire group. It's basically measuring how long it takes for the center of the whole formation to cross the finish line.
All right, so what's the real practical difference here? Let's put these two ideas side by side to really see what makes them tick.
This table really lays it all out. You can see phase delay is all about the individuals, which is fine for simple narrowband signals. But for complex, broadband stuff like music or video, where you have a whole bunch of frequencies packed together, well, that's where group delay becomes absolutely crucial. It's all about the group's overall shape.
So if you remember one thing, let it be this. Phase delay tracks the parts, group delay tracks the whole. And when you're trying to preserve the shape of a signal, it's the timing of the whole that really matters.
Now, you probably saw that bit of calculus in the formula a second ago, that dd omega thing. Don't let it scare you. All it means is that group delay measures the slope of the phase graph. It tells us how the delay is changing from one frequency to the next. And that change is the key to spotting potential distortion.
Okay, so we know how to measure the mess. But what's the goal? What are we actually aiming for if we want to build a perfect, distortion-free system?
And here's the thing that might surprise you. The goal isn't zero delay. That's pretty much impossible. A signal taking a little bit of time to get through a system is totally fine. The real goal is just to preserve its shape, to make sure our team of runners stays in perfect formation. So how do you do that? How do you keep the whole group perfectly intact? Well, you just need one thing, one crucial value, to be absolutely perfectly constant. And that thing is the group delay. And this is the magic trick. This is how engineers pull it off. In what's called a linear phase filter, the delay for each individual runner actually goes up in a perfectly straight line. But because that relationship is so perfectly linear, the slope of that line, the group delay, is a perfectly flat, horizontal, constant value. The group stays together. It's brilliant.
And that's exactly where the name linear phase comes from. It's that beautiful, straight-line increase in phase shift as the frequency goes up. That precise mathematical relationship is the secret sauce that gives us that constant group delay and preserves our signal's shape.
Okay, so we've been talking about runners and stopwatches, but why does this really matter in the real world? Well, it matters a lot. Because without this concept, so much of the technology we use every day would basically just fall apart. Think about it. That crisp, clear audio you love? That's thanks to a constant group delay keeping the bass, mids, and treble from smearing together. That sharp, focused picture on your screen? That's what happens when all the color and detail information arrives at the exact same moment. It's even critical for making sure our data gets from point A to point B without errors. And engineers make this happen with special tools called FIR filters designed specifically for this purpose. So, the next time you experience that perfectly balanced sound or see a crystal clear image, you'll know the secret. It's not just about the notes or the pixels, it's about the timing. What you're really hearing, what you're really seeing, is a team of frequencies all arriving perfectly in step, all thanks to the elegant power of linear phase.